Hey guys, welcome back. Day 21. We're going to talk about solubility, pH, complex ions. So first up is solubility and pH. pH affects the solubility of ionic compounds that contain ions that hydrolyze. For example, I have CaCO3 solid. Well, calcium is a group 2 metal. Calcium does not undergo hydrolysis. However, carbonate will undergo hydrolysis, as we know. And so this will be, we can look up in the back of the book, Ca2 plus aqueous plus CO3 2 minus. KSP here happens to be 4.96 times 10 to the negative ninth. Well, the hydrolysis reaction would be CO3 2 minus plus water going to HCO3 minus, right? Because one of the H's is going to go to carbonate, because carbonate cannot donate protons, doesn't have a proton to donate, and OH minus. And that would be a KB in this case. In this KB happens to be 1.8 times 10 to the negative fourth. It's 1 over Ka2. If we were to add up these two reactions, I would get calcium carbonate, solid, plus water. Carbonate's gone. I get calcium 2 plus HCO3 minus plus OH minus. And this K would be equal to KSP times KB, which happens to be 8.9 times 10 to the negative 13th. So if you look at that, it says K is smaller than the KSP or the KB. Yes. So now the pH, which would be pH, when we think pH, we're thinking the concentration of this or the concentration of this. Same thing. So the concentration of H plus or H3O plus has a relation to the concentration of OH minus, which is right there. So this is where the pH is going to affect solubility of calcium carbonate. If we're basic conditions, so that means there's more OH minus, this is even less soluble. Calcium carbonate is even less soluble because the reaction will go towards reactants. However, if we are in acidic conditions, hydroxide will be removed and more calcium carbonate will dissolve. So that's where the whole pH will affect. Now, if I wanted to neutralize calcium carbonate, I wanted to to neutralize it, I could add this reaction where I have H3O plus aqueous plus OH minus going to 2H2O liquid, and that's 1 over KW. And if I add those up, hydroxide cancels, one of the waters cancels, so my overall new reaction here would be CaCO3 solid plus hydronium. One of the waters is gone, hydroxide is gone, going to calcium ion, bicarbonate, and water. So this green K is the original KSP times the KB all over KW, which happens to be 89. So I go from 10 to the negative 13 to 89. Product favored. Now, not hugely product favored, but it's product favored. So that's how I can dissolve calcium carbonate. And calcium carbonate, the common name of calcium carbonate is limestone. All rain, regardless of what we talk about climate change or anything like that, acid rain, all rain is naturally acidic because of carbon dioxide in the atmosphere. There's always going to be carbon dioxide in the atmosphere. This is not an alarm. There's always going to be carbon dioxide in the atmosphere because plants need it to do their cellular respiration, to make their glucose to then do cellular respiration. So we're going to have carbon dioxide in the atmosphere. And since there is carbon dioxide in the atmosphere, all rain will be acidic. And so limestone will erode. Most fresh water on the planet is acidic. Now, there is fresh water that is too acidic, and that's what we call from the acid rain, which was the nitric acid and the sulfuric acids that end up forming because of air pollution. But without any pollution, all rain's acidic. So this process would happen and it happens slowly over time. Okay. The next topic is simultaneous equilibria. Simultaneous equilibria. This is when we have more than one system in solution. A couple things to talk about. A system is like calcium carbonate going to calcium ion and carbonate anion in solution, or the KSP. That's a system. Water undergoing its equilibrium where it dissociates into the solvent cation, solvent anion. That's a system. Right? Glucose burning and oxygen to produce carbon dioxide and water. That's a system. So any of these chemical systems we have, any KSPs, any KAFs, KAs, KBs, KW, they're all systems. And now we have more than one system in solution. And this goes into, a lot of things that we actually have in life have more than one variable. Way more than one variable. So for example, suppose sodium bromide, NaBr, which is a source of bromide, is added to a solution of silver chloride. What happens? Okay, so I have AgCl in here, and it has a KSP of 1.8 times 10 to the minus 10. Sodium bromide's coming in. Okay. Well, let's see. I got AgCl, Ag plus aqueous plus Cl minus. So I got silver chloride. Sodium bromide. This is soluble. There's no KSP. So that gives me Na plus Br minus. The problem arises, because again, this is strong. The problem arises is that silver chloride has a KSP and silver bromide has a KSP. So if you look at AgBr, Ag plus Br minus, that has a KSP of 3.3 times 10 to the negative 13. So I added a soluble compound to a solution. However, just because it happens with people too. Now, again, human behavior, chemical behavior, not necessarily the same thing, right? There's no thoughts or feelings or, thinking going on. But if some of you guys have friends where if those two friends get together, a lot of times it's going to be unpleasant. You'd be friends with both of them or acquaintances with both of them, especially like in a school setting where you're not necessarily going to one house than the other, but you're just in a bigger area and a cafeteria, a library, or whatnot. Here, I have silver chloride floating around in that solution. So I have silver chloride as a solid in that container. So I just have a solid of it to the side. I got Ag plus floating around and then Cl minus floating around. Well, then we throw in Na plus, don't care about, and Br minus, and now silver has two things to choose from to make a solid. Which one is less soluble? Well, we have AgCl, again, 1.8 times 10 to the negative 10. AgBr, 3.3 times 10 to the negative 13. Because AgBr, silver bromide, is less soluble, smaller KSP, it should precipitate. Let's look. If we do this, I have my AgCl, Ag plus, and Cl minus, and KSP 0.8 times 10 to the negative 10. If we flip the reaction for AgBr, Ag plus Br minus, going to AgBr solid, K equals 1 over KSP. Right, we invert the reaction, we invert the K. Adding them up, silver ion would cancel, and so I would have AgCl solid plus bromide going to AgBr solid plus chloride. And so this K would be KSP for silver chloride, which is 1.8 times 10 to the negative 10th, divided by KSP for bromide, which is 3.3 times 10 to the negative 13. And I get 545. So it's a positive number, yeah. Silver bromide. Now, not all of the silver chloride will dissolve and all of the silver bromide precipitates, but the reaction is favored to do so. It is favored to go in that direction. Last topic is a complex ion. Complex ion, where there is one or more what we call a ligand, which is a Lewis base, coordinate covalently bonded to a metal ion, which is a Lewis acid. Coordinate covalent bond. That's where one atom brings both electrons to bond. So example of H plus OH minus. That's a coordinate covalent bond when that lone pair attaches. So you can think of these ligands, they're bonding to a metal, but it's not necessarily like, hold on, a good analogy would be like a magnet to a whiteboard. You can put the magnet on the whiteboard, you can take the magnet off the whiteboard. So the magnet can be, and it's going to stay on the whiteboard, but with different conditions, these ligands can change. They can substitute and whatnot. So it's more of a Lewis acid-base chemistry than anything else. So let's look at something. Go back to my AgCl. Silver chloride in water goes to silver ion and chloride anion with a KSP. Now, if we add NH3 ammonia to system, to the beaker, the container, well, silver ion plus 2 ammonias, it's a horrible cue, will form this complex with silver and ammonia. And it has a Kf value. So the KSP was 1.8 times 10 to the negative 10. Kf is 1.7 times 10 to the 7th. Overall reaction now would be AgCl solid plus 2NH3 going to, I'm going to put chloride first, and AgNH3 2 plus. That's my complex ion, with the K being KSP times KF, which would be 3.1 times 10 to the minus third, which is a lot bigger. And so you can think of this as silver ion with, you have your ammonias, your nitrogen containing compounds, H, 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 and a lone pair, H, H, H. And what we're going to do is we're going to bond to the metal center on both sides. And that's my coordinate covalent bond. That's all a complex ion is. Now it's time to do some examples. Which of the following compounds are more soluble in acidic solution than pure water? Well, silver cyanide. And so I need to know if I have H3O plus around. So I'm looking for, does my base produce OH minus? Silver is Ag plus, cyanide is Cn minus. So I need a proton acceptor. I'm looking for proton acceptors. Cn minus plus water. We have HCN plus OH minus. Cn is a base. It is an H plus acceptor. So therefore, A will be more acidic, more soluble in acidic conditions than in pure water. How do I know that? Well, let's write it in blue. Ag Cn solid plus, no, just do this. Ag plus Cn minus. Next step, we have right here this going on in black. So the black plus the blue gives me AgCN solid plus water going to HCN and H2O. Whoa, excuse me. So that's A is more acidic, more soluble and acidic. B, lead to iodide, PbI2. I comes from HI, so it's a strong acid. No hydrolysis. So that's an easy one. Aluminum hydroxide. Now this one is more soluble. In fact, this one's special, and this is where we usually I throw in the fact that all metal ions are Lewis acids, but there's also something with this guy. Aluminum hydroxide is special because it's more soluble in acidic and basic conditions. It's special. In acidic conditions, it's obvious because H3O plus will react with that. However, AlOH4 minus is a complex ion. And so that will actually happen. I forget, I think it's above pH 10. It might be pH 12 that happens. So it is a complex. But anyway, since OH minus is a base, aluminum hydroxide is more soluble in acidic conditions. The reaction hydroxide, of course, is more soluble reacts with hydronium. Zinc sulfide, ZnS solid, Zn2 plus S2 minus. Well, that is a strong base. All right, so of course D is. Now, strong bases, just so we know, what are my strong bases? OH minus, O2 minus, because technically speaking that makes two OH minuses in solution, and S2 minus. Those are your three strong bases. So it's your group 1 and group 2 metals, hydroxides and oxides and sulfides. Not all of them per se, but those ones. And then, our 7 strong acids, hydrochloric, hydrobromic, hydroiodic, sulfuric, nitric, perchloric, chloric. They all matter. Next up, number 2, I like this problem. It's the fixing of photographic film. And this is not something we do much anymore, but people used to have cameras where you didn't even know what it looked like until you had it developed. And you had film in the camera, and you actually had to take them to like the drugstore or something to get them developed. You didn't even know what it was. And so this is what happens is silver bromide is very light sensitive, and you dip it into a sodium thiosulfate solution, and you dissolve the unexposed silver bromide, and the exposed silver bromide stays, and you get your films and whatnot. Ghostbusters, I think one of the original Ghostbusters movies has, you can see the dark room where they do this, like a red light. It's interesting. There's two pieces of information that they give us. They gave us a KSP and a KF. We need to calculate the equilibrium constant K for the dissolution reaction and calculate the molar solubility of silver bromide in 0.1 molar sodium thiosulfate. Well, KSP. Well, KSP. Yeah, let's say it's equal to 5.4 times 10 to the negative 13, and that would be silver bromide solid going to Ag plus Br minus. Kf is equal to 4.7 times 10 to the positive 13th. And we just know that we make AgS2O3 2 3 minus. Well, what makes up those things? Well, it has to be silver. And it looks like 2 S2O3 2 minuses, 2 thiosulfates. If we add this up, if I add that up, do I get this reaction up here? I think so, because silver ion cancels, doesn't it? So we get well, keep the K's there. K equals KSP multiplied by KF. Well, it didn't change. And that would be AgBr solid plus silver ion's gone, 2S2O3 2 minus, going to AgS2O3 2 3 minus, and bromide. Okay, excellent. And that K value then would look like, if I do that math, so 25.4. Well, ice table. As long as I have some silver bromide, this will work. What's my original concentration of sodium thiosulfate? 0.1 molar. And as long as we have some of this, we're good. So I have a 2 here, so it's going to be minus 2x, x and x. So at equilibrium, I have 0.10 minus 2x, x, and x. What is my K expression? K looks like it would be the concentration of my complex ion, AgS2O3 2 3 minus, bromide all over concentration of S2O3 2 minus squared. Nice. Let's substitute our numbers in. 25.4 equals x times x up top would be x squared all over 0.10 minus 2x. And that's squared. Oh dear. I got the bottom squared. What do we do? Well, I would recommend square root both sides, which we can do. Square root of 25.4, I got 5.04 equals x all over 0.10 minus 2x. Rearranging, I get 0.504 minus 10.08x equals x, or 0.504 equals 11.08x. So x equals 0.045. Now, what does x represent? X can be here, x is there and there. We are looking for in this problem, I want the molar solubility of AgBr. I want to know the concentration of AgBr. Well, that would also be the concentration of bromide, which happens to be X. So X happens to be 0.045 molar. That is my answer for this case, which is nice. So there you go. Will precipitate form on mixing equal volumes of the following solutions? For A, I got 3.0 times 10 to the negative third molar barium chloride and 2.0 times 10 to the third negative third molar sodium carbonate. Well, equal volumes. That's kind of important. So will precipitate form on mixing equal volumes. Well, we're mixing M1V1 equals M2V2. So if I'm mixing equal volumes, my volume, it doesn't matter what it is, M1, let's say we have 500 milliliters, or it doesn't matter what it is, let's say 500 milliliters, M2, 1,000 milliliters, it's just double, 1 and 2. That means my concentration has to be 2 to 1, it has to half. So when I mix equal volumes, my concentration is halving. So whether it's 25 milliliters, 250 milliliters, 25 liters, 1,000 gallons, it does not matter. If I'm doubling the volume, I'm halving the concentration. Well, what are my things here? My species would be barium chloride, BaCl2, and sodium carbonate, Na2CO3. Well, if they switch dance partners, what do we get? Barium chloride probably is soluble. So my combinations would be BaCl2, BaCO3, NaCl, and Na2CO3. We look, soluble, soluble, soluble has a KSP. And that KSP is 2.58 times 10 to the negative 9th. And you get that by looking it up in your book, in the appendix of your book. Don't just Google these. Why? Because I can vary it just a little bit and make it somewhat close, same order of magnitude, but you get the wrong answer if you do it. We can do that. Sometimes the books do that. So I would always use the book value, just in case. Okay. So now my concentration of barium ion, for A here, concentration of Ba, 2 plus, will be half of that, 1.5 times 10 to the negative third molar. And my concentration of carbonate will be half of that. Concentration of carbonate, CO3 2 minus, is half, and that is 1.0 times 10 to the negative third molar. What do I do with that? Well, barium carbonate, barium 2 plus, CO3 2 minus. Right. Q is equal to concentration of barium times concentration of carbonate. So QSP would equal 1.5 times 10 to the negative third multiplied by 1.0 times 10 to the negative third. So QSP looks like it's 1.5 times 10 to the minus 6. Well, KSP, I used that color, KSP is 2.58 times 10 minus 9. Q is much bigger than K, so that means the precipitate forms. So for A, and this is A, precipitate forms. B, it's the same thing. So for B, QSP would equal, the concentration of barium's half that, which I'm just going to say 0.5 times 10 to the negative 5. And half of that would be 2.0 times 10 to the negative 5, because it's still barium and it's still carbonate, sodium nitrate soluble. So QSP would be 1.0 times 10 minus 10, which is less than KSP, so it's no precipitate. Number 4. In an excess of ammonia, copper 2 ions form a deep blue complex ion, CuNH3,4,2+. I'm always going to give you what the complex ion is. You don't have to memorize them. And the formation constant is 5.6 times 10 to the 11th. We're going to calculate the concentration of Cu2+ in a solution prepared by adding 0.005 moles of copper 2 sulfate to half a liter of 0.4 molar ammonia. Okay, so we have 0.005 moles of Cu2+ sulfate in 0.500 liters. This is soluble. That means we have 0.01 molar CuSO4. So since this is soluble, the CuSO4 goes to Cu2 plus SO4 2 minus. So we have 0.01 molar copper 2, and that's what we care about. Cu2 plus aqueous plus, it looks like there's what, 4 NH3, and that goes to CuNH3 4 2 plus aqueous with KF. Ice table. Initially, I have 0.01 molar. Actually, I have just one fix, 0.1 molar copper 2. And we have 0.40 molar ammonia and nothing. There's a change. Well, K is quite large, isn't it? 5.6 times 10 to the 11th. So we're going to assume it all reacts. So we're going to assume all reacts. Minus 0.01 minus 4 times 0.01 plus 0.01. So none. 0.36 molar and 0.01 molar. And that's beautiful. Because KF is 5.6 times 10 to the 11th. And the KF expression would be concentration of Cu NH3 4 2 plus Cu2 plus NH3 to the 4th. My question to you is, can this number here, this 0, go in that number there? I don't think it can we? That cannot be 0. All the math teacher friends, including my boss, would not like that. Can't have 0 on the bottom. So what do? Here, what we're going to do is that we assume a small back reaction. So we get Cu2 plus 4 NH3 we're assuming it's going this way, CuNH3, 4, 2 plus. Another ice table. So initially I'm going to have 0.10 molar copper ammonia complex. I'm going to have 0.36 molar ammonia and no copper 2. I'm going to use X, we haven't used it yet, minus X, plus 4X, and plus X. So we have X, 0.36 plus 4X, and 0.10 minus X. Plug it into the K expression. Because again, Kf is equal to my copper 2 complex ion all over copper 2 plus and H3 to the 4th. 5.6 times 10 to the 11th equals 0.10 minus X, and 0.36 plus 4X to the 4th power. Now what can we do with these X's? Well, I have 0.1, so 10 to the negative 1, 10 to the 11th. I can approximate this to 0. And then negative 1, 10, yep, I can approximate that to 0. So we approximate, and that makes our life a lot easier. Approximate, I get 5.6 times 10 to the 11th equals 0.10 all over X times 0.36 to the 4th. Well, I can solve for X, can't we? X equals 0.10 divided by 5.6 times 10 to the 11th and 0.36 to the 4th. So X, which equals my copper 2 solution, copper 2 ion concentration, is 1.1 times 10 to the negative 12 molar, which is very, 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 very small. However, we have, just so you know, I have half a liter. And we know in that 1 liter, I have 1.1 times 10 to the negative 12 moles. And 1 mole happens to be 6.022 times 10 to the 23rd Cu2 pluses. So that gives me 3.3 times 10 to the 11th Cu2 plus in the container. So times 9's a billion. That's 300 billion copper 2 ions in that container. Even though we think it's almost all gone, it's still quite a bit there. That's about as hard as it gets with these complex ion formation. What did we do? We assumed, since K was big, that it all reacted, and we saw a small back reaction. So we assumed a small back reaction and did a nice table kind of backwards and solved for X. X was what we were looking for, and that's it. So that's going to end complex ions and pH and solubility. Hope that worked out. Reach out to me if you need me. Take care, guys. Bye.